I'm Bill Gropp, Director of the National Center for Supercomputing Applications at the University of Illinois and Vice Chair of SC20 Invited Talks. Welcome to the SC20 Invited Talks session on Extinction Rebellion. The overarching theme of SC20 is more than HPC. Complementing this theme, the Invited Talks collectively focus on applications and technologies impacting all areas of science, engineering, medicine, and society. Around SC19 last November, global efforts collectively labeled Extinction Rebellion captured our imaginations. HPC, from its inception, has played a central role in enabling breakthroughs in climate and weather modeling and environmental science. The distinguished speakers in this session will enlighten us on how our community can contribute to inter- and multidisciplinary research initiatives with broad scientific and societal impact for future generations. Patrick Heimbach is a professor at the University of Texas at Austin in the Department of Geological Sciences. He is a member of the core faculty in the Odin Institute for Computational Engineering and Sciences, where he holds the W.A. Tex Moncrief Jr. Chair in Simulation-Based Engineering and Sciences. Patrick's main research interest is understanding the general circulation of the ocean and its role in the global climate system. Patrick serves on the U.S. National Academy of Sciences Ocean Studies Board, the National Science Foundation's Advisory Committee for the Office of Polar Programs, and on NSF's Advisory Committee for Cyber Infrastructure.
Thank you very much for giving me the opportunity to talk about how computational science and supercomputing can support ocean science. My topic today is augmenting a sea of data with dynamics, the ocean's data and parameter estimation in support of climate research. I'd like to begin by emphasizing that climate change is fundamentally ocean change. The reason here is that more than 90% of the Earth's net radiative heat imbalance ends up in the ocean to lead to ocean warming. Roughly 30% of the anthropogenic emission of carbon dioxide is absorbed by the ocean, leading to ocean acidification, and all of the water that is provided from the melting of the polar ice sheets, Greenland, Antarctica, and glaciers and ice caps contributes to a global sea level rise. Just last year, the Intergovernmental Panel on Climate Change has issued a special report on the role of the ocean and the cryosphere in the changing climate. And this is just a schematic summary of the report that shows a number of physical indicators such as ocean heat content increase, ocean acidification, ocean deoxygenation, sea level rise, increasing marine heat waves, and among a number of sea ice decline in the Arctic, among just a number of indicators. We haven't even talked about ecosystem indicators in this graph. So clearly, understanding the ocean changes and potentially mitigating some of these changes to lead to a more sustainable ocean is a global challenge. And the United Nations has declared the period 2021 to 2030 as the United Nations Decade of Ocean Science for Sustainable Development, and to address the science we need for the ocean we want. The question that we may ask here is, how can computational science and supercomputing support this decade effort to make this a success and to lead to a decade where we really have, for example, a well-predicted ocean that we can work with. So this begins by asking the question is whether ocean science is a big data science. Clearly it feels that way. We have a range of satellites that are monitoring the Earth system, but more so you might answer the questions yes, because we are today able to simulate the climate system and its components such as the ocean with increasing detail, meaning resolution, complexity, meaning process understanding and representation, to create vast amounts of output for these simulations. So this simulation is the Arctic coupled ocean sea ice system at what we call eddy permitting resolution. We see these mesoscale eddies, the swirls in this animation. These are the ocean's analog of the atmospheric weather systems. They are much smaller scale because of the density difference between the atmosphere and ocean. So eddies, much smaller scale systems than in the atmosphere. And making sense of these vast amounts of model output is clearly a big data problem. And it's a challenging problem. Simulations give us unprecedented access to time-evolving phenomena of the ocean, that is consistent with our theoretical knowledge as encapsulated in the equations of motion. We should also recognize that the ocean is a turbulent fluid and therefore has a continuum of space and timescales of processes that are supported by the ocean. So what we see here, a figure of some of these oceanic processes: gyre circulation, diurnal overturning circulation, the El Nino southern oscillation phenomenon, baroclinic and barotropic adjustment processes that are governed by wave processes on a rotating sphere, all the way to Ekman transport and Ekman processes, deep convection in the subpolar oceans. They act on this continuum of timescales here that we are in meters to the circumference of the Earth on the x-axis, and then on very rapid timescales here that are seconds to minutes, all the way to very long timescales. Clearly, what this suggests to us is that there is no real spectral gap in the system, such that we have to assume that high wave number, high frequency motion, so that means very fast motion at small scales, will ultimately impact and inform the low wave number, low frequency motion that act more on climate timescale, meaning seasons, years, and centuries. So the lack of a spectral gap also means is that either we represent all of these processes, or we need to provide a cutoff and then parameterize some of these processes. A very strong and just very recent example here is a paper that was just published last month, and that talks about the internal waves and how internal waves in the ocean drive and control the turbulent mixing in the ocean, which in turn is an important ingredient for the global overturning circulation, which sets some of the climate phenomena in the ocean and its interaction with the overlaying atmosphere. So small scale, high frequency motion that ultimately govern some of the important climatic processes. An example of the impact of such internal waves and internal tides is this regional simulation in the subtropical North Atlantic. This simulation has been forced not only with the atmospheric forcing, but also with the astronomical tides. And output here is produced now not just at daily output, but at hourly output, which allows us to see these internal wave motions propagating here, and they are encapsulated in the kinetic energy density that we're calculating here. We see more larger scale motion, which is the mesoscale field, and phenomena, of course, is the Gulf Stream and its separation into the North Atlantic. So these simulations have been performed at 4-kilometer horizontal resolution, and it is clear that such simulations at these very high resolutions are expensive. Just to give you an idea, 2 examples: the global scale simulation at 4 to 7 kilometer horizontal resolution. One simulation year with hourly output would require roughly about 220 terabytes of output and about 1.6 million core hours. And depending on your domain decomposition, you're looking at the usage of somewhere between 5,000 and 30,000 cores. Going to even higher resolution, but in a regional context of the Arctic, here at 1 to 2 kilometer resolution, you're looking at 7.6 million core hours and 1.1 petabyte of output, and requiring somewhere on the order between 10,000 and 80,000 cores, depending on how well your model scales as you tile up the Arctic or the planet into an increasing number of such tiles. So clearly, these calculations are very, very expensive calculations. This figure here has been drawn by Baylor Fox Kemper. It shows as a function of the year that we're in, the ocean model resolution, for example, here for the different climate model generations. So the FAR stands for the first assessment report that was conducted in the late 1980s. And all the way to the 6th assessment report of the IPCC that we have in 2020, 2021. You see as a function of time how we gradually were able to increase the horizontal resolution of the ocean model component, but that increase has been relatively small. It has not kept up with Moore's law, so with the theoretical computational capabilities. And furthermore, we're nowhere are these resolution anywhere near to be either mesoscale resolving or even internal wave resolving, which we if we continued this projection just in a linear sense, we would arrive somewhere in the years 2040 to 2060s. So bottom line of this is that, yes, we need to really improve our capabilities to resolve these very, very important scales, but we also need to improve our capabilities to achieve well-calibrated estimates of the ocean state based on all the knowledge that we have, and the ability to continue to run these models at coarser resolution with very good parameterizations or calibrations. So this brings us to the second uncertainty. The second problem is that we deal with uncertain inputs. These are initial and boundary conditions. So this can be framed as the initialization problem. And of course, parametric and structural model uncertainties that require comprehensive model calibration. It has to be pointed out here that these parameter spaces that we're seeking to calibrate are potentially very, very high dimensional parameter spaces. And the question is, how do we make progress and to perform such comprehensive calibration efforts? So we're asking the question is, what aspects of the simulations are robust? How do errors accumulate and propagate over space and time? And how do we quantify those? Clearly, we need observations to ground theory and simulation, even with improved model resolution and process understanding. So this brings us back to the question, is ocean science a big data science? And perhaps the answer is also no. And the reason for being somewhat pessimistic here is looking at the in situ capabilities. So the ability from in situ instruments from 1950 to 2010 as a function of depth to cover the larger parts of the ocean. So the top panel here is the northern hemisphere, a summary plot. The lower plot here is the southern hemisphere. And we see that it's only in the early 2000s that we're beginning to have a fairly recent fractional coverage of observations up down to 2,000 meter depth, both in the northern hemisphere and in the southern hemisphere. But keeping in mind that the mean depth of the ocean is actually 4,000 meters, so we're still not even covering half of the ocean in terms of its volume. What is more is that what we see here is the observational fractional coverage as a function of latitude and depth. So these are the different color ranges, represent the different depth ranges. But in green here, we see the volume of the global ocean, and we see that where the largest fraction of the ocean volume is not where the largest fraction of ocean observing is. So this basically drives home the point that from a purely observational perspective, oceanography remains today a sparse data science. So we have two incomplete knowledge reservoirs, the one of an eclectic global ocean observing system, and then the other one, though, the ability to use numerical models that encapsulate our physical understanding, but that require uncertain inputs, such as initial condition or parameters. And the question is, can we optimally combine these two knowledge reservoirs? Can we do so in a manner that provides useful for climate analysis, meaning, for example, causal dynamical attribution, detecting small residual changes? Can we provide measures of uncertainties with these estimates? And can we use simulation to inform efficient observing system designs strategies, given that it is very complex to perform such observational campaigns? And it is here that computational science and engineering comes into play. It is an essential driver for progress in science, in applications where experimental or observational approaches are very costly, very slow, very dangerous, or even impossible to do. And clearly, ocean science in general, and even some of the regional oceanography, for example, polar oceanography, fits many of these criteria very well, given the fact that it's very difficult to access some of these polar regions, and the instruments have withstand much more tighter physical ambient environments in order to conduct these measurements. I'd like to present to you today one of these efforts, which is the Estimating the Circulation and Climate of the Ocean, called ECHO. ECHO is a multi-platform, multi-instrument synthesis effort that integrates ocean and marine ice observations with models, meaning with the equations of motion. It's an effort that's led today out of JPL, includes a number of national partners, such as the University of Texas, MIT, and AER. Scripps Institution of Oceanography, plus international partner. It's a NASA-supported effort that also, in that sense, tries to bring together all the different NASA remote sensing assets into a coherent picture of the evolving ocean state. This is shown here. So ECHO is learning from sparse heterogeneous observations and models. We have our different observational assets here in terms of satellite data. This is satellite gravimetry, the GRACE and GRACE follow-on mission. We have the series of satellite altimeters from TOPEX Poseidon to the JASON series that measure sea surface height quasi-globally with unprecedented accuracy. We have satellite microwave radiometer that measures quantities such as sea surface temperature. They can measure sea ice properties. And then on the right-hand side, we have a number of what we call in situ assets. For example, autonomous Argo profiling float, of which there are 4,000 today in the world ocean, measuring the hydrographic properties of the water column. These are ship-going observations through the GHOST ship program, previously the World Ocean Climate Experiments program, where ship go across basin and take temperature salinity measurements top to bottom and water sample of the as they drive along, all the way to elephant seals, which carry these little logger where again temperature salinity are measured, and along with telemetry these data are submitted to satellite, and we can use them especially in environments here in the Southern Ocean that would be otherwise inaccessible, at least with today's technology. So bringing together these different data streams with a model often is referred to as a form of data assimilation. There's two nice, very succinct ways to characterize what data assimilation is about. So ideally, all observational data streams are interpreted simultaneously with the process information provided by the model, which leads to a consistent picture of the state of the system that balances all the observational constraints, taking into account all the respective uncertainty ranges. Or, put more recently by Steve Penny, data assimilation allows information provided from sparse observations to be propagated in time and space to unobserved areas using dynamical and physical constraint imposed by numerical models. So to show you how we are conducting data assimilation in this what we call 4D VAR framework or adjoint framework, I'd like to make a comparison here between backpropagation-based neural network training versus adjoint-based model calibration and estimation. So in a machine learning context, we are faced with a neural network where we have inputs. These inputs are propagated through several layers of a neural networks to outputs. And these outputs are then compared to training data, yi. And the goal of the training consists in minimizing this loss function, which basically minimizes the misfit between the propagated state of the system and the training data itself. The way how this minimization is achieved is by training, so to speak, a high-dimensional space of these weights of the neural network. And to achieve this, we seek the gradient of this loss function with respect to all of these weights. The very efficient way to calculate this gradient is through a method that's called backpropagation, which basically propagates the sensitivity of the output, meaning the loss function, to all of these weights. And this gradient can then be used in gradient-based optimization to achieve such a neural network training. Well, coming to model calibration and state estimation, something very similar can be done, where now our loss function is replaced by a model data misfit function, a least squares misfit function that's given by this J. And then this model data misfit function is extended through this term here, which is the Lagrange multiplier methods, where we impose the model dynamics. Model dynamics is shown here. So the model steps the state at time k forward to state at time k plus 1. So in our optimization, this is imposed. And you can think of replacing the layers of the neural network now with a different time step of the model. And what we're training, what we are looking for is the sensitivity of this misfit function with respect to all of these certain uncertain inputs. These could be the initial conditions of the model, these could be external forcings, or these could be model parameters. And so the adjoint, in the same way as backpropagation in neural networks, we're looking at the sensitivity of this output loss function to all of the inputs or control variables, and the backpropagation is conceptually extremely similar to the adjoint model that calculates these sensitivities here. So in summary, so ECHO is learning arguably from the most complete set of available ocean observations and known physics and dynamics by solving a gigantic least squares model data misfit minimization using this Lagrange multiplier method. The dynamical model that is used in this context is the MIT general circulation model. It is an approximated form of the Navier-Stokes equations for an incompressible fluid on a rotating sphere. Comes in with a lot of features that it has, for example, scalable domain decomposition. But really one of the most important feature in our context is this adjoint code generation via automatic differentiation. That's maybe today in machine learning might be called differentiable programming. So the way that this model has been written is been kept and is compatible with these general purpose automatic differentiation tools that provides a very, very powerful way to both generate the adjoint model and to keep the adjoint model also up to date with new model development. I'd like to now shift gear a little bit and demonstrate and show you how these adjoint models and these gradient information can be used not only for optimization, which is what, of course, the main topic, but they can be very powerfully used for interpretation, understanding, and for doing science. And so I call this beyond optimization. So we are looking at science application with the adjoint itself, and for the purpose of, for example, understanding sensitivities of climate quantities of interest. An example here is the causal or dynamical attribution of South Atlantic Ocean circulation. So what we are looking at here is a map of the South Atlantic, here the exit of the South Atlantic into the Southern Ocean. We have here the South American continent and the South African continent. The latitude here is about 34 south. And what we have here is a number of mooring arrays. And what we are interested in is to understand the heat exchange and the volume, the mass transport in and out of the South Atlantic Ocean. So we can measure these exchange processes are varying in time, and we'd like to both understand this time variation of these mass and heat exchanges in the South Atlantic and see and attribute these to the different contributors from, for example, both local forcing changes and also remote forcing changes. And the way that we formulate this problem is that we're looking at this mass transport at 34 south as our quantities of interest, and we are asking the question, how is this sensitive to a very high dimensional control space that is given, for example, by surface atmospheric forcing perturbations everywhere in the domain or by initial conditions back in time. So again, the same conceptual framework applies. We can use the adjoint model to propagate the sensitivity information from the time when we observe, where we pose these quantity of interest anomalies, and then propagate this to the adjoint or dual state back in time and to all of the forcings of the state back in time. What this looks like is an animation like this one, where we see, this is shown here, the sensitivity of mass transport at 34 south, for example, to the zonal wind stress anomalies everywhere in the domain as a function of time, and we go back in time. And you can see in this animation that as we go further back in time, the region of influence extends, of course, beyond just the local 34 south section. We can see patterns that we understand very well from an oceanographic perspective, because they are a superposition of wave adjustment processes, waves that act in a fluid on the rotating sphere. These are Kelvin wave, equatorial Kelvin wave, coastal boundary waves, and Rossby wave propagation. And all of these wave propagations are very, very well teased out through the adjoint model and basically shown here in the simulation. This, of course, is only one of a number of different ways to look at this problem. So we've just looked at the sensitivity of this transport to zonal wind stress. There are other components, the marginal wind stress, the net heat flux, precipitation. All of these forcings are very powerfully computed with just one sweep of the adjoint model and allow us to produce these sensitivity or heat maps and to do a dynamical understanding. We can go even further with this. We can use the sensitivity information as sensitivity kernels for convolution integrals in which we can do linearized reconstructions of these sensitivities. A second important application is the uncertainty quantification and formal observing system design. And I've mentioned before that uncertainty quantification in particular remains a computational challenge to provide because of the recursive dimensionality, the different ingredients that uncertainty brings into the game. So in the context of data assimilation, uncertain ingredients are, of course, the observations themselves. We have measurement error, we have representation error, we have irregular sampling in space and time. We have the assimilation scheme, the data assimilation algorithm itself and its approximations, how are data ingested into the data assimilation system. We have model parametric uncertainties and structural uncertainties, for example, through discretization errors or model inadequacy. We have all the boundary conditions that we require to solve the equations of motion, for example, external forcing, the bathymetry, and lateral boundary conditions. And finally, we have, when we look at this from a Bayesian perspective, we have the use of prior knowledge in form of the prior error covariance and representation error. So one way that we can pose the uncertainty quantification and observing system design problem is through the use of derivative information, meaning the adjoint of the Hessian of the model data misfit to jointly account for the model, the observations, the forcings, the prior knowledge, and all of their uncertainties. How do we do this? Well, let's go back and consider in a simplified manner here our model data misfit function. And let's look at the linearization of this model data misfit function, which gives us here the sensitivity operators. This is the adjoint model. This is the tangent linear model that it brackets the prior error covariance, and comparing this operator to the exponent of a multivariate Gaussian distribution, it becomes clear is that what we end up here is a formulation of the posterior model error covariance. And the posterior takes into account the model dynamics and the impact of the model, of the observations and the observational errors on providing a posterior error covariance. Geometrically, what we're doing here is if we're looking at this misfit function in the simplest way, sort of a squared misfit function here, in a high dimensional space of uncertain parameters. Let's pick out one parameter here, for example, R1. We see a high curvature, so a Hessian second derivative, that's the curvature. High curvature basically tells us that the observation that we're looking at provide a very strong constraint on this direction in our uncertainty space. On the other hand, in green here, R2 is a very low curvature, which means that the observation that we have provides very little information to constrain the system. So the uncertainty problem then is sort of a two-part. So the one is the uncertainty reduction that is provided by the observations on the one hand side. But now we are interested in an unobserved quantity of interest that might be a metric that we are not directly able to measure. And we say, how do the reduced uncertainties in this uncertain space of input parameters help us to reduce the quantity of interest? We can exercise this approach or this problem in the concept of the recent observational program that's been a joint observing program by the US and the UK, overturning in the subpolar North Atlantic program, or called OSNAP. It consists of a range of mooring arrays here in the subpolar North Atlantic. We have here the Labrador Sea and the boundary currents of the Labrador Sea where moorings have been placed. We have, this is to the east, the west of Greenland. To the east of Greenland, we have the Erminger Sea and another set of mooring arrays all the way across this mid-Atlantic ridge to Scotland. This array system, this array system has been designed to measure really the changes in the poleward mass and heat transport, but also the freshwater transport out of the Arctic into the North Atlantic proper. And this measurement array, of course, is a very complex array to do. And the question is, can computational science provide insights onto the design of such an array? The conceptual framework here, this has been work by Nora Lose, consists of a workflow that begins with the uncertain inputs that are driving an ocean circulation model, a data assimilation procedure where we achieve a reduced model data misfit, and the Hessian, the second derivative of this model data misfits, provides us with a measure on how the prior error covariance is reduced to a posterior error covariance. So in a first step, that's the prior to posterior uncertainty propagation, leads us to better constrained inputs, and then we can use the model to then propagate these reduced uncertainties onto quantities of interest, for example, Nordic Sea's heat content that we're interested for a number of reasons, to improve our understanding here and to reduce the uncertainty in this Nordic Sea's input. And the question is sort of how can we quantify what type of observational assets are really contributing to this reduced quantity of interest uncertainty reduction. So the example shown here shows a number of observational assets here in red. So we have subsurface temperature in the Erminger Sea, it's theta A, and theta C is surface temperature. We have subsurface temperature measurements, hypothetical, here off the coast of Portugal, and another subsurface measurement here in the Denmark Strait overflow. As I've said, the sensitivity information is a very important ingredient for the Gauss-Newton estimate of the Hessian, of the second derivative of the posterior. And we can look at, so first, the sensitivity of the quantity of interest to all of these uncertain input fields. Here is shown again the wind stress, the meridional wind stress sensitivity. And then on these four panels here show the sensitivity now not to the QI, but to the different observational assets here. So this is the sensitivity of the subsurface temperature in the Erminger Sea. We have sensitivity of the off Portugal subsurface temperature. We have surface temperature in the Erminger Sea, and then here Denmark Strait overflow. So all of these sensitivities computed with derivative information of our general circulation model provide us with these patterns. And these patterns can now be projected onto the pattern of the direction of interest. And what we can say is that the better these patterns project onto the sensitivity, the quantity of interest, the more we can say that the observing system provides a constraint on the quantity of interest. This is encapsulated in this very simple equation here, but take note here that these gradient information are very high dimensional, 10 to the 8 dimensional gradients here of the quantity of interest sensitivity, and then here the observing system sensitivity. And so we have a very, very complex projection onto these other, which ultimately gives us a measure of the dynamical proxy potential of the different observational assets for the QOI. But this scalar product is now weighted by this factor D here, which is a rescaling by what we call the sensitivity to noise ratio, which is a dynamical analog to the statistical signal to noise ratio, but now weighing these dynamical sensitivity against the noise, for example, from the observations and from the prior that we encounter here. So it's a condensation of a very complex algorithmic framework that takes into account Hessian eigenvectors, which point to the most potent observational constraints and give us the direction of the subspace of the uncertainty space that is well informed by the observations versus the subspace that is ill constrained by the observations. Coming towards the end, I'd like to highlight here again, so we've started from a forward model simulation, which is of course the workhorse of computational science, that we develop physical models for the system that we seek to simulate and predict. But we augment and enhance these forward simulations with optimization inverse methods in order to provide comprehensive model parameter calibration and state estimation frameworks. We would like to endow these forward simulations with robust uncertainties, for which we then need to provide the uncertainty quantification algorithms. And for sparse data systems, we would like to provide this entire modeling change from forward simulations to inverse simulations to guide observing system design on this one end. And from the other end, we are coming from the data science perspective, where when we do have large and very big data problems, to see how we can bring scientific machine learning to bear to connect with these model simulation-based approaches. And the question is, how do we do this? How do we harness the explosion of some of the data to extract knowledge where we have them, insight and decision, and combine them with the parts of the model equations where we do not have that much data? The approach here, the one that I would like to advocate for, is to bring together concepts from big data science and sparse data science, or computer science and computational science, or again, scientific machine learning versus simulation-based science. So how can we bring those concepts together? What's been shining through the talk here was the idea that gradient information that we can obtain from the equations of motion on the one hand side, or from the neural networks, to see whether we can sort of combine these concepts. And the concepts here, the overarching concepts, are that of differentiable programming of our of our physical models or the neural network models, and the notion of general purpose automatic differentiation, which would allow us to couple together backpropagation and adjoint models, and to use deep learning algorithms as surrogate models that are naturally embedded within physical and dynamical models for hybrid machine learning. So this leads me to conclude. I'd like to thank really a large group of people that has been instrumental in this effort. This is the ECHO group, the Cryos group here at UT, and friends and other places. This is a picture from a recent team meeting. Really, these people are making these concepts and this effort happening. So I conclude with putting up this slide that really is a nice conceptual and philosophical summary on how we use these two end members, observations and computational models, and together with uncertainty quantification to improve our knowledge, and that leads us to robust decision making. And I finish, and happy to take questions. Thank you.